So to define the next kind of integral we're going to be working on, we need to define a new term, a new property of a surface, and that's orientability. Right? So let's say we have a surface S. Right? So a definition here. An orientation on a surface S. What this is a choice of unit normal vector field on S. All right, that is a vector field on the surface S such that at every point of S it gives a vector which is perpendicular to S and has magnitude 1. Right, so let's kind of sketch what this should look like. Well, actually, let me give you a fact first before we sketch. The fact. If a surface is orientable, it has exactly 2 orientations. Ah, I can't spell. There's no S in it. The beginning of has. It has 2 orientations. Right. Okay. So a surface is orientable if it has an orientation, of course. So what does this look like? So let's draw the same surface 2 times if I can here. That's pretty bad. Clean that up a bit. Let's do it this way. Yep. And let's try and make this almost the exact same surface here. So pretend these are the same surface. You get rid of that extra little bulge there. All right. So what do the 2 orientations look like on this surface? Well, we have the one that's kind of upward, or it points in some sense outward. Right. So this is, imagine you have this kind of helmet here and it's a bunch of spikes sticking out of it. Right? You've probably seen these funny bicycle helmets that look something like that. The opposite orientation is just turn all these vectors around. So they're all going inward to the surface. Right? So that's, the painful helmet to wear, where it has a bunch of spikes going in, and you put it on and you're not going to have a good day. So these 2 orientations are, of course, related. Let's call them, let's say the 2 orientations are N1 and N2. Right? These are related by, well, one of them is just the negative of the other. Right? Which is really quite convenient. Okay? So how do we get our hands on these orientations? Well, remember, if we have this parametrization here, we can create a vector field on the surface, a normal vector field by RU cross RV. Okay? So this guy here is a vector field which is perpendicular to the surface S. So the orientations are given by, again, we're going to assume here S is parameterized by R of UV. Right? So the orientations are given by the following 2 expressions. and I have RU cross RV, right? Divide by the magnitude of that. Okay, so that makes sure that we have a unit vector. So this is a unit normal vector field on the surface. Then the opposite one is the negative of that. And we can get the negative of a vector field by just reversing, or of a cross product by just reversing the order. So that means the other one is just RV cross RU over the magnitude of that. Right? And I just want to point out again, this is really just the negative of this guy. Right? So that's what orientations look like. And now we'll erase this real quick and talk about another definition for surfaces. Before the next definition, let me just give you a caveat on the statement that if a surface is orientable, it has two orientations. This is true, but it should really say a connected surface. If it's or for a connected surface, if it's orientable, it has two orientations. Right? If the surface is disconnected, then on each piece of the surface, you have a choice of two orientations. So you should try counting if you have, say, a surface with n disconnected pieces, how many possible orientations. But anyway, that aside, each connected piece only has two orientations. All right, and now let's define a new property. Right, so we talked about closed curves before when we're doing, say, the fundamental theorem of line integrals and Green's theorem. These are very important to have closed curves. We can ask now, what is a closed surface? Right? So definition, a surface is closed if it is the boundary of a solid. Right? That's kind of the easiest way to think about what a closed surface is. Right? You could also say, it's compact and has no boundary, but for us and for our purposes, say a surface is closed if it's the boundary of some solid object. So examples of that, so let's say some examples are the sphere, right? The hollow sphere, of course, right? And the sphere is the boundary of the solid ball, of course, right? So the sphere is an example. Another example is an empty box. Right? That's another example. Right? So let me just say here, sort of empty, wow, there's an E in empty now. Empty box. Okay? And to give you something a little more fun, another example is a torus, right? Which is like a hollow donut shape. Looks something like that, right? So this is like a tube that's connected back to itself, right? So again, a hollow donut, right? Non-examples would be, let's say I take a sphere and poke some holes in it, or cut out a disc. Let's say I take this empty box, but I pull off one of the faces of the box, right? Those are some examples of non-closed surface, or surface which isn't closed. Okay, so what's the point of defining a closed surface? Well, this lets us talk about what is the positive orientation, right? So definition, on a closed surface, so on a closed surface, the positive orientation is the outward pointing one. Right? Is the outward pointing orientation. Right? So let's say on the sphere that I already have drawn here, the positive orientation on the sphere would be the one like so. All right. Just think of it kind of like a ball with a bunch of needles coming out of it. All right. So then the negative orientation, of course, would be the one where all the needles are going inside. All right. So that's just some terminology here, and see you in the next video.